Motion Part 2, Maximum Speed, Distance, and Freefall Motion. Now we're going to be looking at maximums and minimums involving motion. Now remember, when we find max and mins, we're looking for extrema, which occur at critical points. Now, if the endpoints are included in the question though, don't forget to check those as well. So our first example will be given a position function, and we're looking for the maximum distance the particle travels from the origin. So obviously, since we're looking for maximum distance, we're looking at the maximums of the actual position itself. So what we need to do is first off find its derivative and solve for 0. That way we'll know where any critical points are. So in this case, its derivative velocity will be negative 32t plus 48. Now again, because we want to look for possible places where max and mins happen, we'll solve this for 0 to discover where any critical points may happen. Now when you subtract 48 and divide by 32, it works out to be a time value of 1.5. Now what we can do here then, of course, is plug back in and figure out if it's going to be an actual max or min. And essentially, if I start my sign chart here at 0 and go indefinitely out, checking the signs of velocity, when I plug any number between 0 and 1.5 in here, it does give me, in this case, a positive value. And then if I plug any number after that, it's going to give me a negative value. So clearly this will be a maximum. Now, we may know where the maximum occurs, in this case 1.5, but the question was asking for the actual maximum distance. So what we need to do is we need to take the time 1.5 and plug that into our position function. That way we'll know the actual distance that was, location of where its maximum was at. So in this case, plugging 1.5 into our position function tells us that the maximum distance away from the origin is 28. Now let's look at a situation again given the same function, except now we're looking at the maximum speed of the object. So in this case, because we're looking for the maximum speed, we want to find the derivative, velocity, which talks about speed, and then find the maximum of that. So again, as we just did, the velocity here is going to be negative 32t plus 48. Now, as before, since we want to now find the maximum of the velocity, we should find its derivative. So in this case, we'll actually be looking at acceleration for any possible critical points. Now, because the acceleration here works out to be negative 32, that means there are no critical points at all. But if you look again at the question, it was a closed interval. And so in order for us to figure out where the maximum speed may happen, it's going to happen at one of the endpoints, again, as no critical point exists. So what we want to do is we want to calculate the velocity at 1/2, and we also want to calculate the velocity at 2. Now we are going to take the absolute value of them, of course, because we want to neglect the direction in which they're traveling, and we just want the actual speed itself. So in this case, if I plug 1/2 into our velocity, we get a value of 32. And if I plug 2 into velocity, we get a value of 16. So that tells me that the maximum speed is going to happen, in this case, at time equals 1/2, right at the beginning of the interval, and the speed was 32. Now the last area we want to look at is the concept of freefall motion. Here we'll be looking at motion that is happening on Earth, in which an object is simply thrown up or down with some initial velocity and moves along a vertical line. Now for simplicity, we're going to assume that gravity is the only force that's actually acting on the object, and we'll neglect the size of the object. So anytime we do one of these situations, we want to create our position function, okay? So obviously we have s of t. So the s sub 0 right here, this is going to be our initial height. So wherever the object begins before it's either thrown upward or dropped or whatever, that's where it starts. V sub 0, again, with the sub 0, it is an initial value. This is going to be the initial velocity. Now, in this case, it can be 0 because we may simply let it go and let it fall. Or if it's thrown upward or initially thrown downward, you can have positive or negative values for that initial velocity. Now, the last part right here, this g, this is going to be our gravity constant. Now, this will be one of two different numbers depending on how the motion is measured. So if it's measured, for instance, in meters per second, the gravity constant here is going to be 9.8 meters per second squared. Okay, so again, you're going to have to read the question very carefully to realize how this is being expressed. Now, if, for instance, we choose to measure this, for instance, in like feet per second or something like that, then what they're going to do is we're going to have to let the gravity constant be 32 feet per second squared. So the acceleration of gravity is certainly constant, but we're going to have to use different numbers depending on how we're labeling and talking about, the motion we actually have. Now, it is important to understand that sometimes initial height may be 0, sometimes initial velocity may be 0. Sometimes some of the most simplistic freefall motion problems, gravity may actually be the only force acting upon it. So you just be prepared for that. Now, if that is the case and you don't actually have initial height, any position you calculate after letting it fall will always be a negative number. So you'll just have to realize that from wherever you started with, that negative number is the distance it's fallen from its original position. Okay, so looking at our first example here, we're looking at a baseball player throwing a baseball into the air, straight up into the air at 100 feet per second. And we'd like to calculate how high the ball will travel. So again, in this case, we've got to find all the little pieces to create our position function. So first off, our position function here, s of t, is going to equal 5, because as it said, it was released from 5 feet above the ground. That's going to be our initial height. Now, because the ball was thrown at 100 feet per second, that's going to be our initial velocity. Now, it looks like, because they're talking about feet per second, that our gravity constant, the 1/2 thing here, is going to be 32 t squared. So we can go ahead and clean this up just a little bit and make this look like 5 plus 100t minus 16t squared. So this right here is a model for the position of the baseball at any given time after it's been released from 5 feet above the ground at 100 feet per second. Now again, the question we're looking for is how high will the ball travel? So that sounds like a maximum. So what we should probably do is look at the derivative, solve for 0, and that's probably when it will happen. And then just like our previous example, we can plug this back in to find this actual max height. Now this also makes sense on another level, because if I take the velocity, which is again is the derivative, which in this case would be 100 minus 32t, if I take that and solve for 0, what I'm really doing is saying what is that instant in time in which the baseball stopped moving? And that makes sense because when it's initially thrown up at 100 feet per second, it's going to start slowing down immediately as gravity is pulling back on it. And it's going to reach its maximum height as soon as gravity finally overcomes all that velocity it was initially imparted with. So by solving for 0, we're going to find that instant in time where it peaks and just stops for an instant before it starts returning back to Earth. So in this case, again, solving for 0 tells us it happens around 3.125 seconds. Now remember, this is when it happens. So our job, of course, is to find out exactly how high it traveled. So the last step here is to go ahead and plug that back in our position function. So in this case, if we take our position function and we plug in 3.125, it tells us that the maximum height of this baseball is 163.25 feet. Now in our last example, we'll look at a very simplistic idea of a calculus textbook falling off a water tower. Now, when you read the question, that's all you're given. There's no initial velocity. It was simply dropped off the water tower, but it also doesn't really include how tall the water tower is. So when we create this position function to work with, we're simply going to have to work with gravity and only gravity. Now, that does mean whatever we plug in or work with will always be a negative number, so we'll just have to interpret that negative number as how far it's fallen from the top of the water tower. So in this case, again, we have 0 initial position since we don't know it. We have 0 initial velocity as it just fell off the front. So this is going to be our position function of negative 1/2. And for this problem, since our previous example was done in feet, we're going to go ahead and do this one in meters per second. So we'll let our gravity constant be 9.8 t squared. Okay, so again, if I just clean this up a little bit, we can refer to this right here as negative 4.9 t squared. So now the first question we're looking for, of course, is how fast is the book falling after 2 seconds? So since we're looking for a question of speed, we want to go ahead and calculate what the velocity is. So in this case, our velocity is going to be negative 9.8 t. And once we have that, we can plug 2 into it. But not only that, we want to plug 2 into it and do the absolute value, because again, we're simply looking for speed. So I take it back. Because speed is basically how fast. We know the direction is going to be negative as it's falling downward. So we're just going to look for speed. So we'll take negative 9.8 times 2 and take the absolute value of it. And that's going to tell us that after 2 seconds of falling, the textbook is reaching a speed of 19.6 meters per second. Now, in our second question, we'd like to know, how far has it fallen after only half a second? So in this case, it's the same sort of idea, except we're going to be looking at a distance problem. So going back to our position function here, so s of t, and again, that's going to equal negative 4.9 t squared. If I want to discover how far it's fallen after only half a second, all we have to do is essentially plug that into our position. Now, I do want to go ahead and throw the absolute value on here, just because as we do this, I want to make sure that even though the answer is supposed to come up negative based on how I wrote it, we're just going to look for a pure distance idea. Because obviously, we don't know the height of the water tower, so we're just going to express this as that amount of distance having traveled. So we're going to take the absolute value of negative 4.9 times 0.5 squared. And again, because we just want to know how far this thing's traveled altogether. So when you calculate that, this comes out to be 1.225 meters. Now for our last question, we'd like to do a little bit of a different calculation. Here, I would like to know how long it would take the book to fall 50 meters. So again, we're simply going to use our position function. So again, this is that negative 4.9 t squared. But again, this time what we have to do is ask ourselves the question, when is this right here going to show that we've fallen 50? Now again, because our model doesn't have that initial height, we have to use this as a negative 50. Because obviously having fallen 50 meters, the value would be negative 50. So by plugging that in for our position, we're going to have to solve for time. So when I divide and square root, the time where we hit that value is approximately 3.194 seconds after it falls off the water tower.